Hello, in this lesson we will learn how to solve exponential and logarithmic equations. We will use the properties of exponential and logarithmic functions to solve a variety of equations and learn strategies that will help us determine when solutions are valid. Let's begin by looking at the objectives for this section. In this section, we will start to learn how to solve simple exponential and logarithmic equations. We will also solve more complicated exponential equations and more complicated logarithmic equations. Finally, we will use exponential and logarithmic equations to model and solve real-life problems. As we move through the lesson, pay attention to the strategy being used in each example. In this section, we will learn how to solve equations involving exponential and logarithmic expressions. There are two main methods that we will use, the one-to-one property and the inverse property. Let's briefly review these properties. The one-to-one property tells us that if two exponential expressions with the same base are equal, then their exponents must also be equal. Likewise, if two logarithms with the same base are equal, then their arguments must be equal. This is the one-to-one property. The inverse property reminds us that exponential and logarithmic functions undo each other. Notice the examples at the bottom of this slide. In part A, because both sides have the same base, we can set the exponents equal. In part B, because the logarithms have the same base, we can set the arguments equal. In part C, the natural logarithm is used to undo the exponential function. And in part D, we rewrite the logarithmic equation in exponential form. Remember that the natural logarithm, written as ln, has a base of e. When solving exponential and logarithmic equations, there are three common strategies. First, rewrite the original equation so that we can use the one-to-one property of exponential or logarithmic functions. The second is to rewrite an exponential equation in logarithmic form and apply the inverse property of logarithmic functions. And the third is to rewrite a logarithmic equation in exponential form and apply the inverse property of exponential functions. As we work through the next examples, think about which of these strategies is being used. Let's solve the first exponential equation. Notice that both sides of the equation are powers of e. Since the bases are the same, we can use the one-to-one property and set the exponents equal to each other. This gives us a quadratic equation. After moving all terms to one side and factoring, we obtain two possible solutions. The solutions are x equals -1 and x equals 4. Now let's look at part B. First, divide both sides of the equation by 3. This leaves us with 2 raised to the x equal to 14. Since 14 is not a power of 2, we cannot rewrite the equation using a common base. Instead, we rewrite the equation in logarithmic form. Using the change of base formula and a calculator, we find that x is approximately 3.807. Now let's solve an exponential equation that has a quadratic form. Notice that the first term can be written as the quantity e to the x squared. Once we rewrite the equation, it resembles a quadratic equation and can be factored. Factoring gives us two factors. Using the zero product property, we set each factor equal to 0. The first factor gives us e to the x equals 2. Taking the natural logarithm of both sides gives us x equals the natural logarithm of 2. Using a calculator, this value is approximately 0.693. The second factor gives us e to the x equals 1. Taking the natural logarithm of both sides gives us x equals the natural logarithm of 1. Since the natural logarithm of 1 is 0, the second solution is x equals 0. Therefore, the solutions are x equals 0 and x equals the natural logarithm of 2. Notice that the graph confirms both solutions because the curve crosses the x-axis at those two values. Now let's solve logarithmic equations. In part A, we have the natural logarithm of x equal to 3. To remove the logarithm, we exponentiate both sides using base e. Since exponential and logarithmic functions are inverses, the logarithm disappears and we are left with x equals e cubed. Now let's look at part B. Notice that both logarithms have the same base. Because the logarithms are equal and have the same base, we can use the one-to-one property. We simply set the arguments equal to each other and solve the resulting linear equation. This gives us a solution x equals 2. In this example, the logarithm is multiplied by 2. The first step is to divide both sides of the equation by 2. Now we have a logarithm equal to a constant. To eliminate the logarithm, we rewrite the equation in exponential form. This gives us 5 squared equals 3x. Solving for x gives us 25 thirds, and this is our solution. When solving logarithmic equations, we must always check our answers. This is because logarithmic equations are not defined for all real numbers. The expression inside a logarithm must always be positive. In this example, we begin by combining the logarithms using the product property. Next, we rewrite the equation in exponential form and solve the resulting quadratic equation. Factoring produces two possible solutions, x equals 5 and x equals -4. At this point, both values appear to be solutions algebraically. However, before accepting them, we must check them in the original equation. After checking, we find that x equals -4 is not valid because it makes the argument of the logarithm negative. Therefore, the only solution is x equals 5. Let's verify the result graphically. The graph shown represents the original logarithmic expression. Notice that the graph crosses the x-axis only once. The x-intercept occurs at x equals 5. There is no x-intercept at x equals -4. This confirms what we found algebraically. The value x -4 must be rejected because the logarithmic expression is undefined there. Therefore, the only valid solution is x equals 5. This concludes our lesson on solving exponential and logarithmic equations. Thank you for watching, and I'll see you in the next lesson.